So quickly answering a question from one of you. So when we looked at potential, at real potentials, we looked at the flow around the cylinder when the uniform flow was in this direction, right? And to create the flow around the cylinder, we say, okay, we're going to add a dipole here. And so now that we needed a dipole, if you think about the streamlines of the dipole had to be in this direction. They were like this, right? Of course, far away, then you have the uniform flow that pushes everything. But if you really zoom into the center of the dipole, so inside of the cylinder, where usually you don't care about the flow because you're just looking at the flow outside of the cylinder, but you would have streamlines which look like that, okay? Now, when we first introduced the dipole, we brought a source and a sink close together. And I wrote a vector which was a dipolar moment, which was 2q times the distance between the two on the x-axis, and that corresponds to this. It corresponds to how you bring your two sources and sink together, and then you get this picture for the streamlines. Right? Now, you can bring those two together from different orientations, right? You can bring them together like this, right? And then you get this picture. Now, what we saw from complex potential is that, in fact, if your flow has an angle, so here my flow has an angle, right? Then when we look at the dipole, we do not get a dipole which is in the x direction. We get a dipole which is tilted. Our dipole is like this. So let me just show you briefly. So whenever you're in doubt, you can always go to the MATLAB routines which you have. Okay, so look at this. So here I have a uniform flow. It's only in the x direction. Okay, and I have a dipole which is also in the x direction. And so when you compute the flow, you see that, I mean, it's hard to see because you don't directly see the streamlines, but you get an idea that really these are the streamlines for the flow around the cylinder. Right? I would have to be able to really get to, well, maybe I can try and plot a bit more streamlines, but I cannot guarantee that we'll get exactly onto the streamline, which is the circle, right? But if you plot more streamlines, then you see like, you see here, I don't have the streamline exactly, which is the cylinder, but you see it's really, you see that here in between there is a streamline, which is just the surface of our cylinder. Do you see that? Yeah, okay. Now, your dipole is just a way to represent your flow, right? So if you put like a flow with an incoming angle, let me show you that. And now I don't know how I program my dipole, so I'm not going to, I will update that to make sure you can actually play around with it. But for now, you have to just look at this. So let's say if I put a uniform flow which has an angle, so now it doesn't only have a component in the x direction, it also has a component in the y direction. And so if I put 1, 1, that means that my flow is incoming with a 45 degrees angle, right? And I'm just going to keep my dipole the way it is. So my dipole is like that. Right? You'll see that I no longer represent the flow around the cylinder. A dipole in this direction is not, is not enough. Do you see that? So here, I'm just plotting a few streamlines, but you see that this is no longer the flow around the cylinder. I'm not even sure. Actually, the weird thing is that from here it's quite clear, even, that you don't have any close streamlines. You will not have a streamline because this is bizarre, but some of the flow which is coming from here gets sucked in, if you want, into the sink, which is the part of the dipole, and some of it comes out of here. So this is very unphysical. Yeah, do you see that? So this flow represents nothing. You actually need to put the right dipole, and of course you need to put a dipole which is tilted. Yeah? If you put the right dipole which is tilted, which I don't think I have programmed in there, then you'll get back to a flow around the cylinder. So your dipole is really just whatever you put inside to make sure you impose your right boundary condition. Okay? And remember, your dipole can have a direction. Okay. Now, so let's continue that. So I'm going to have streamlines whenever theta is equal to k pi divided by n. Okay. Now let's see what n can be anything, right? But we'll start with numbers less than 1, between 1/2 and 1. Anything between 1/2 is actually just strange, so we won't discuss that. But let's say that we have n. If n is between 1/2, so, and 1. So what we'll do is just limit and see what happens when n is equals to 1 to 1/2, and what happens when n is equals to 1/2. So when n is equal to 1/2, then theta is equal to, my streamlines are when theta is equal to 2k pi, right? So how many k's can we use? We can use 0 and we can use 1. So the only streamlines that we have really is just theta equals 0, essentially. Now you see that? So the only streamline that we have, we just have one, and it's this one. The one I applied before, theta equals 0. Theta equals 0 or 2 pi is the only streamline. So this here will represent the flow around a sharp peak. Right? This is a streamline. Now you could compute, and actually it turns out that the flow around the other streamlines would be like that. So analytically it's important because it tells you what happens when the flow goes around a sharp angle, right? So you could, for instance, compute now the velocity. So when theta equals to 1/2, then, so this is here. Our potential, our velocity is equal to theta 1/2, 1 divided by z to the power 1/2. Okay. So what do you see here about, what do you know about the velocity at that point? Right? You see that your velocity, the magnitude of your velocity, if you write z as a complex number, as an argument, and if I write z as, again, the c0 doesn't really matter so much here. It will be square root of r exponential minus I theta divided by 2. It doesn't really matter. But when r goes to 0, you see that the magnitude of the velocity vector goes to infinity. Right? So for potential flows around a sharp corner like this, for the velocity to sort of circle around this sharp corner, you know, the velocity here is going to go to infinity. At that point here, we have a singularity. Singularity, the magnitude of the velocity goes to infinity. Do you see that? This is actually why you have to impose the cutter condition at the trailing edge. When you make sure that you have, you know, if you don't impose the cutter condition, then in the picture that I showed, this is exactly the same physics of what you have. If you don't add circulation for the flow around an airfoil, then your streamlines look like this, right? And here, when the flow has to go around the trailing edge, actually it's the same for the leading edge, but for the leading edge it's a bit less unphysical, even though it is unphysical. But here you have to, your velocity goes to infinity in one direction, and then it moves to infinity in the other direction. And you don't want that, right? But what would happen is exactly this flow here. You see that? Yeah? Okay. And so for any, actually for n between 1/2 and 2, 1.5 and 1, then what you will have is you will have two streamlines, okay? And it will look like this, right? So if n was a bit larger than 1/2, you would have two. You can convince yourself of that, and I'll show you how they look like. they would look like this. You would have one here. Remember, this one is always a streamline. Theta equals 0 is always a streamline. And the other streamline would be here. Okay, well actually let me not put an arrow here because this is confusing. And then that would be the flow around, that would represent the flow around a sharp corner which is not that sharp, but which goes like that. Okay, this is for n between 1/2 and 1. And then for n larger than 1, then you have the flow in a corner. So let's look. Let's do n equals to 1. If n equals to 1, then what do we have? I have my potential, right, which is equal to just C0 times Z, right? So what is that potential? Huh? Is it what? So straight lines, so what I don't like about this is that a straight line is neither a vector field nor a function. Right? So let me ask it differently. So to what flow does this potential correspond? Huh? Yeah, over a flat plate, but actually we've seen that before. Huh? You've seen that. You should recognize it. Right? It's a constant times Z. This is the uniform flow. Yeah, we've seen that before. Yeah, so if you take the derivative, you just get C0, and C0 here is actually your uniform flow. So it's the same as having, so in this case, what you have is, yeah, Z equals 0 is a streamline, but also so theta equals 0 and theta equals pi are a streamline. Now everything here is assuming that C0 is real. You don't have to assume that C0 is real. If C0 is not real, then everything just tilts by an angle. Right? So this is here. This is back to our uniform flow. Uniform flow, right? So here, what do we have? We have this here, which is a streamline, and this here, which is a streamline, and really, all of your streamlines are just like that. Yeah. And then when n is larger than 1, then you have those two which are streamlines, and the flow you're interested in is really this flow around the corner. So you have the flow in a corner, coming from one direction, right, being deflected to another direction. So those plots are bad, and I'm just not putting too much effort in it because you have other MATLAB routines that you can play with, which are the one for the flow around a corner. And so here, what I'm doing is I'm plotting as a sequence. So don't really look at time. Time doesn't matter. Time is just a parameter. So I'm going to go from 0.5, from n equals 0.5, so from when equals 1/2. Gradually, I'm going to increase it to 3. Right. So you're going to have 1/2, and then a bit more than 1/2, up to 1, and then a bit more until 3. And so those are the different flows that you represent. I think it's plotting just the vector fields. Okay. So red are the streamlines that you get from n theta equals k pi, or theta equals k pi divided by n, and here n is equal to 1/2. So you do have this flow, right, around a flat plate, but the flow is coming in this direction on the bottom, and it just has to go around this very sharp interface, this very sharp corner, I should say. And at that point here, you have a flow singularity. You have a velocity that goes to infinity. Right? If your velocity goes to infinity, what happens to the pressure? It goes to minus infinity, right? So that means that you have an enormous suction at that point. Right? This is what you, okay. So this is what so here at this point here you have a singularity. Now, when you increase n a bit, so here n is between 1/2 and 1. And that's the example when n is between 1/2 and 1. Then don't look at the flow between those streamlines. The flow between those streamlines represents nothing. Right? Forget about this here. Whatever is represented here is not really physical. So you just look at whatever is outside. So you see here you have the flow which comes along this plate and again has to turn around this sharp corner to move in this direction. Yeah. Again, at this point here, you will have a velocity that goes to infinity. Right. So if you saw anything like that, usually in a flow field, then what would happen in reality is that at this point, of course, you don't expect flow to be able to do this because of viscosity. Because of viscosity, what will happen is at this point you will have flow separation. Right? Here, from this point, you're going to have a streamline that goes in this direction, and you have flow separation. Right? If you have flow coming from this direction and that direction, then at this point also you have a streamline which is attached, and this is what we discussed as the cutter condition. Yeah? Okay, so here if you continue increasing the value of n, then you still have the flow around sharp corners. This is flow around sharp corners. Yeah? You still have point infinity here. This is when you reach n equals 1. You have your uniform flow, and this is when n gets larger than 1. So don't look too much at the flow here. Actually, the flow here is not good, but the one here and the one here, both of these are fine. So if you continue just looking at this quarter here, you see that this is the flow inside of a corner. Right? So flow which are deflected. So the flow is coming at an incident angle, and now it hits a flat plate and goes like that. Okay. At this point here now, what happens to the velocity? You may not see it, but it goes to 0. Right? So the velocity here will go to 0. You can see that from the potential. Right? If now, let me go back to this slide. If now n is larger than 1, right? Say n equals 2, for instance. If n is equal to 2, then when you differentiate and get to the velocity field, what is your velocity field going to be? It's going to be c naught, 2 times c naught times z. Right? The z goes to the numerator now. So when z goes to 0, your velocity goes to 0. Right? So in a corner, you have an ideal flow in a corner. Sorry, back to MATLAB. The ideal flow in a corner. In the corner, you have 0 velocity. If you have 0 velocity, what happens to the pressure? You have a stagnation point, so you're going to have a higher pressure there. Yeah? Okay. So we're done with that. Yeah, I don't have time to do the flow around the flat plate, so I'm going to skip that. Maybe just briefly, I'll mention it next Tuesday. And I'll just code a few MATLAB routines so you can play with this. So I really encourage you, if you are uncomfortable with those flows, right? What people used to do with complex analysis, because you can just do with MATLAB. You just change the different numbers until you sort of get an idea for how the flow looks like. And you have all the routines available. You can put an irrotational vortex here, one here, a source there if you want, a sink there, a dipole. Just look what the flow looks like and what happens. Look what you just maybe try it. Try and do stuff. If you put a sink here and a source there, or if you put like sink, source, make sure all of whatever mass comes out of the source gets potentially sucked into a sink, yeah? Because otherwise you're adding mass to your system, which is not really what you want to do. But then try and create flows. It's like a challenge to yourself. Can I just try and get the flow around something which would look like a profile, right? You would want to put dipoles of changing magnitude maybe, and irrotational vortices also of changing magnitude if you want circulation around your profile, right? So just try until you sort of see how these things work. Okay? That's the equivalent of just defining a complex potential and trying to draw streamlines with conformal maps. Okay. So we're done with that, and now we're going to stay with ideal flows, but we'll change geometry. Okay, so this is part 6. So now we're leaving the plane, and we're going to discuss 3D axis. So people call it 3D, but it's not really 3D. It's more 2D axisymmetric. So just so that you see visually the difference, up to now, we discussed ideal 2D planar flows, right? And what these really represent are just flows in 2D, when essentially up to now we have discussed ideal 2D planar flows. So in terms of applications, that represents the flow around an airfoil. Right? A wing is long enough that you can assume not much happens in the z direction, and so if you're looking really at what's happening in the flow, you just look at a cross section, and then you have a 2D planar flow. So I have even a little picture for that, so that this really marks where's my Dropbox? Oh, whoops. Hold on, now I'm... Was it here? Yeah. I'll put both at the same time. Okay, so here, this, whoop. Can I move that? No. Alright, maybe I'll just use this mouse. It's gonna be easier, I think. Oh, I inserted it in the same. Let me just delete that. Okay, so this here, this is, you know what this is. I'm only saying you know what this is because I forgot the name in English. This is a sailplane. Now I remember. This is a sailplane, right? So it has wings, and it has very long, it has very long wings, and therefore, not much is happening in this direction. A little bit is happening in this direction, but you're almost in the 2D plane, and really, the flows we've been looking at represent flows in those cross section here, right? Now, if you're in the frame of reference of the sailplane, then we have an infinite flow coming from this direction, and the flow goes around the wing like this. This here is our 2D planar flow. Yeah? You may not realize, but actually it turned out really good this year. Last year was a disaster. Like the way I drew it, I think you can actually guess what we were doing. But last year it didn't work so well. Okay, so this is, do you get that? This is the flows we've been looking at for now. And now, what we're going to discuss now, those are 3D axisymmetric flow. And so these are 3D flows, but not really 3D flows, but the flows we'll discuss are flow around more slender objects. So around a Zeppelin, for instance. Of course, showing those images borders on the politically incorrect, but there was a time where they were built a lot, and that was what it is. Okay, so here the flow we are discussing is if you are in the framework of this long elongated body, then you have an incoming flow from this direction, right? And if you think about in the plane, the streamlines are going to look a bit like this. Right? So they go around the object. Now it's 3D because you have flow in all directions, but really it's axisymmetric, right? So I'm just showing you that because the way we're going to represent the flow in that case is always, I cannot represent it this way, so we'll just cut through and it will look like 2D planar, but it's not 2D planar. Right? It's axisymmetric. And they represent two very different kinds of objects. Yeah, the tools are the same, right? Everything is the same, except like, you know, when you think about those and when you're trying to solve it, you always have to remember, okay, this is not an elongated plane. We are looking at the cross section. It's really an oblong thing, and also looking at cross section. So this is what we'll discuss. Okay, so 2D. So this is potential, ideal. So we'll discuss the potential and the streamline. Now, because we've streamlines, because we have already discussed in much details the fundamental physics around these in 2D planar flow, there is nothing new. It's just the geometry which is different. Okay, the geometry is different, but there are two things. There are two take-home things. Is that because the geometry is different, it turns out that the mathematical trick of complex functions does not work for that geometry. So really, just complex potentials is really just a mathematical trick. And it works because you can map out the 2D plane with complex numbers. You cannot map out this circular geometry with complex numbers, and so you cannot use complex numbers if you're dealing with that kind of geometries. So anytime you have a potential flow, it's a potential flow, but it's an axisymmetric potential flow, so it's a 3D potential flow, then you cannot use the mathematical tools of complex potentials. You have to go back to the real potential and to the stream function. So let me remind you again, we're still within the same problem. So we still have a irrotational flow, and we still have an incompressible flow. So the Laplacian of phi is still equal to 0. And now what we are going to write are the potentials and the stream functions. Actually, I'm not going to write them. I'm just going to write everything inside of the. I'm just going to copy what's in the book for 3D axisymmetric flows. Now, it's important that we agree on notations, because in that part, I think what you will struggle the most with are the notations. So once you are in 3D axisymmetric flows, there are two coordinate systems which you can use. You can use cylindrical coordinate systems, and you can use spherical coordinate systems. Now, the spherical coordinate systems you will most of the time only use if you essentially have one source or one thing at the center, or if you're trying to represent the flow around the sphere, which is the example we will do. The cylindrical coordinate system is the one that you would use if you were trying to represent the Zeppelin, for instance. Okay? So you need both. So let me write. So on the left-hand side, I'm going to put cylindrical coordinate systems. So this is just a summary. Yeah? So we've seen most of that already. We've discussed streamlines. We've discussed complex potentials. We've discussed not complex potentials. We've discussed potential. So we know that the velocity field is the gradient of the potential. So I'm just going to here rewrite all of the formulas which we've already written somewhere in the class in a different form. On the left-hand side, we'll put cylindrical. On the right-hand side, we'll put spherical. So the cylindrical, the thing is both for the cylindrical and for the spherical now. It's a sort of a convention, and it's what they do in the textbook. So I'm going to follow what they do in the textbook. They put the uniform flow in the z direction. Okay? And it's coming from the negative z direction, because this is what makes the analytical solution the easiest. And so for cylindrical coordinates, you'll see, and now I'm going to put my z-axis. Usually you have the z-axis pointing up, but now I'm going to put my z-axis pointing to the right, and the flow is going to come from the left. Okay? So just so we agree on notation, so z is going to be here, z. So I have x. Hold on, I'm getting confused. X, y, z. Okay, so x is into the board. So that here is going to be our reference frame. And every time when we have a uniform flow, usually it's going to come from here. Okay, this is our uniform flow is going to come from here. It's going to be the same in cylindrical, in spherical coordinates. Okay, now for cylindrical, it's not too crazy. I think I will quickly draw here in the little corner how we would usually define cylindrical coordinate system, and then I'll draw the equivalent because it's easy to represent here. Right? Usually, your cylindrical coordinates, you have a point here, right? You project this point onto the xy plane. And then this is your polar angle. This is the distance to the z-axis, and that is your z-coordinate. Yeah, this is cylindrical coordinates. So we'll use the same notation. Let me make sure I'm not saying something. Does the book use theta? What did I put? No, actually, this is why I did that, because the book doesn't use theta; it uses phi. So let's make sure we don't do that too confusing. So phi is this angle, and that is r. Yeah. So when you report that onto that coordinate system, then if I have a point here, it has coordinate r, phi, and z, and so the angle phi is this one, r is the distance to the z-axis, and z is that coordinate. Okay, so keep that in mind. Huh? So phi is an angle in the xy plane. Is that clear? Okay, because all the formulas are going to be written in terms of that. Now, in spherical coordinate, again, usually the spherical coordinates if you have a point here, right? The spherical coordinates are represented a bit differently. R is the distance from the origin. This is the angle theta from the z-axis. And then when you project onto your xy plane, this angle here, I forgot its name in English, but the notation the book uses is phi. Yeah? So the angle where you have axis symmetry is phi in spherical coordinates when you do a potential forward spherical coordinates. So now I'm going to represent it with the z tilde. So this is a bit. Hopefully this will. We have this point here, and my point is represented by r phi theta. Then my angle theta is the angle from the z-axis. Yep. This here is my angle theta. And then when you project your point onto the xy plane, then this angle here from the x-axis is your angle phi, and r is the distance to the origin. Now it didn't go so well this time, so I'll refer you to the book. You know, it's harder to draw in this direction than the other. Eh? So remember, those two images are the same. This one and that one, they are the same, except I put the z-axis here in the horizontal direction. So it's easier to see here. R is the distance from the origin, theta is the angle from the z-axis, and when you project it here, and phi is the angle from the x-axis. Okay. Here phi is the angle that determines the axis symmetry. So nothing is going to be a function of phi, right? Just like nothing here, when we have cylindrical axis symmetry, then nothing is going to be a function of phi. Right? So these are our coordinate systems, and now I'm just going to write the formulas. So the potential flow. Once you have your potential phi, you know that your velocity u is equal to the gradient of the potential, right? That means that your velocity is only going to have a component here. In cylindrical coordinate, your velocity only has a component in the radial direction, and it has a component in the z direction. Right? Your velocity never has a component in the hoop direction, because we have axis symmetry. Okay? So the gradient only has non-zero component in the radial direction, and the r component is equal to d phi dr. This is just the gradient of this is just a definition of the gradient, and it also has a non-zero component in the z direction, and the component is equal to d phi dz. Same for if you're using spherical coordinate systems. Again, u, we're not changing the physics of our problems now. U is still a potential flow. And here, your velocity is going to have only components in also in the radial direction. So the direction here, pointing outside of the board, and in the direction defined by the angle theta. So in this direction here, but not, again, not in the hoop direction, not in this direction here. Right? And ur is equal to, again, d phi r, and u theta is equal to 1 over r d phi d theta. This is your potential. And let me give you the expression for the stream functions. Those we've seen also before, but that was at the very beginning of the class. I'm just going to nicely summarize everything here, so you have everything at the same place. So the stream function here, this is now the Stokes stream functions. ur is equal to minus 1 over r partial psi over partial z, and uz is going to be equal to 1 over r partial psi over partial r. And if you have the stream function for, and you write it in spherical coordinates, it will be ur is going to be 1 over r squared sine theta partial psi over partial theta, and theta is going to be minus 1 over r sine theta partial psi over partial r. Okay, so those are all the formulas you need to go from velocity field to stream function and back, and to go from potential to velocity and back. Now you don't have a complex potential, so you cannot nicely have one complex formula for just the potential and the stream function. They're just separate. So those are the formulas that you need in axisymmetric flow. And the next thing I'm going to do is just write down our fundamental flows. Okay, so the fundamental flow in 3D axisymmetric flows are very much the same as what we had for planar flows, but there is one exception, and we'll discuss why. Is it this? Oh no. Hold on. Sorry, I'm trying to. This is just a print of what is in your book, because I don't want to rewrite all of that. So you'll just get it from your book as well. So here are our fundamental flows. So your fundamental flow, we have the uniform flow in the z direction. You have your source and your sink, and you have your dipole. Okay, so we have the three same, and those are the formulas. And I'm not going to tell you how, you just do the exact same thing as what we did for cylindrical, and you'll find these. For instance, if you think about the potential around a source, right? Now it's not Q times log of R, it's Q divided by R. Right? Why is that? Like, think that you'll get to the velocity field if you differentiate with respect to R. So your velocity field is going to be in 1 over R squared. Yeah? Which is what you need, because now your flow, if you're thinking about your source now is not just you don't have volume coming out only in the radial direction. It's not just like this, it's like this, but also towards you. So when you write your control volume, you have to write a control volume which is now a sphere, right? And if your volumetric flow rate is constant through a sphere, then this is just going to be Q. The volumetric flow rate is U times the surface of your sphere, which is 4 pi R squared. And so you see that your velocity U is going to be in Q divided by R squared. So this is why your potential has to be, for a source, has to be 1 over R, if you want to take the gradient and have a velocity which is in 1 over R squared. So this is exact, and the 4 pi, which is not a 2 pi, comes from this 4 pi here. This 4 pi here comes from this 4 pi. In cylindrical coordinate, we had 2 pi R. And this is why. So I won't go into any details of that. You need to those are just formulas which will be given in the exam. You can also put them in your cheat sheet, no problem. But you just use them the exact same way as what we did before. You superpose. Right? Now, there is one which we had in 2D planar flow, which we don't have here. Which one is that? The irrotational vortex. And the reason is, there are two reasons. So number one, if you think about the flow route of Zeppelin, in this direction here, there will never be a circulation. There is not a lot of physical mechanism to allow for circulation. The flow is just going to go around, and that's what the flow is going to do. You don't have much lift if you're throwing like an arrow, right? And you don't put wings on the arrow. You're just throwing something which is really slender, like this, right? If I throw that, there's not going to be a lot of circulation in this direction, which will give me lift. There's going to be very little lift. You need something which is, you need surface. You need a bit of 2D planar flow in order to create lift. So that's the number one reason. And the second reason is because, if you think about circulation by default will not give you an axis symmetric flow. You cannot have circulation in this direction and circulation in that direction and have axis symmetry. If I'm just taking a cross section of my Zeppelin, this is my cross section, and I have circulation, that would mean that I have a net. I have this, right? By definition, this is not axisymmetric because in this direction is going like this, and in that direction, and here underneath is going like that. This is not axisymmetric. I need the same to happen both on the top and the bottom, right and left. So by definition, a vortex, if you had circulation along this direction, is not that it cannot exist, but then it's not axisymmetric. So you cannot represent it with axisymmetric potentials. Yeah? Okay. I think I'm reaching the end of my time today. So unfortunately on Tuesday, we will still have to do some ideal flows. We'll do the flow around a sphere. That will be just the example we do in class. There are other examples for you to work in your homework, which will be posted today. And we'll discuss, the last topic we'll discuss is unsteady flows, unsteady potential flows, which is unsteady potential flows. You can have that in 2D planar or in 3D axisymmetric flows, but we'll do it in 3D axisymmetric flows. Okay? Just because that will give you another example in 3D axisymmetric flows.